Hi there. In this series of lectures, we are going to look at the classical problem called leader election, which has been useful in many variants of distributed systems, including today's cloud computing systems. In this lecture today, we'll see what the leader election problem actually is. So let's start with an example. Suppose your bank account details are replicated at a few servers that are maintained by your bank. But one of the servers that the bank maintains is responsible for receiving all the reads and writes from a client, such as ATMs or the banking application on your iPad or the banking application on the website, and so on and so forth. So this single special server that is on the bank side is called the leader server among the replicas. Okay, so the leader is responsible essentially for coordinating the replicas. Now, there are several scenarios that can happen with a leader. There might be two leaders per customer. This might be problematic because now the group of replica servers is not sure who the leader is, and therefore reads and writes might be split across these multiple leaders. Servers might also disagree about who the leader is. Some servers might know server A as a leader, and other servers might consider a different server as a leader, and that server might not even think it's the leader. And this might again lead to inconsistency in the system. If the leader crashes, then this means that the clients may not be able to send reads and writes to the system, and once again you may need to re-elect a new leader in the system. So each of these scenarios that I've described as a question leads to either inconsistency or unavailability in the system. Some more examples of situations which require a leader. We discussed the different types of multicast ordering, and one of the ways of implementing total ordering for multicasts was to use a sequencer process, and this was a special elected process from among the group of processes itself, and there needed to be exactly one sequencer process. Okay, this sequencer is essentially the leader. If you have multiple sequencers, then total ordering may in fact be violated in the group. When we discuss time synchronization, we discussed the network time protocol, also known as NTP, and the NTP organizes all the servers into a tree, and there is one server at the root of the tree, and you need to elect who this server is from among all the potential NTP root servers. Other systems in industry that also leverage leader election include open source systems such as Apache Zookeeper and also Google's Chubby system, on top of which a lot of Google's internal systems rely on. Essentially, in a nutshell, a leader in a process group is useful for coordination among the processes in the group itself. Typically, these processes are servers in a cloud. So in a nutshell, in a group of processes, we want to elect a leader. One of the processes needs to be elected as a leader to undertake special tasks such as coordination. Also, it's not just sufficient to elect a leader and let the leader know about it. You need to let all the other non-leaders in the group also know who the leader is. So these are the two requirements of the leader election protocol. Now, what happens when this leader crashes or it fails? Well, first of all, some process detects this failure. How does it detect this? Well, it detects this using, say, a failure detector, using any one of the failure detectors we have seen elsewhere in this course. You could also use other mechanisms, as we will see some of our systems do. But what happens after you detect this failure? Well, after this failure is detected, then you need to run another election algorithm so that a new leader is elected, and this leader is a non-faulty process, meaning one that has not crashed. And also you need to let all the other non-faulty processes in the group know who the new leader is. So that's the goal of the election algorithm. That's the leader election problem in distributed systems. So once again, when someone gives you a problem, just make sure that you know what the system model is under which you're trying to solve the problem. Essentially, the system model tells you what the assumptions are. In this case, our system model consists of n processes. Each process has a unique ID. For instance, it's IP address and port number. Messages that are sent from one process to another are delivered eventually. They may take a while, but they're delivered eventually, and they're delivered reliably. Failures may also occur during the election protocol. So for instance, while you're trying to elect a leader, the leader might itself fail. The next would-be leader might in fact fail, or one of the other processes in the system might fail, and the leader election protocol needs to be tolerant to such failures. So a few more requirements from the viewpoint of the election itself. Any process should be able to call for an election. Why is this? Well, first of all, any process in the system may detect the failure of the leader, for instance, via the failure detector. Most failure detectors allow any process in the system to detect the failure, for instance, heartbeat-based failure detectors or gossip-style failure detectors. When a process detects that the leader has failed, it can initiate an election, which essentially means it calls for an election. A process can call for at most one election at a time. We don't want multiple elections running simultaneously. If multiple processes call an election simultaneously, we want all of those together to yield exactly one leader. We don't want them to yield conflicting leaders. But at a time, you want only one election running. Also, the result of an election must not depend on who calls it. So the initiator's ID, whichever process initiated the election, that must not influence the outcome of the election itself. Instead, the outcome of the election must be based on certain other criteria that are important to the system or are important to the application. So a little bit more formally, a run of the election algorithm must always guarantee two properties at the end. The properties are safety and liveness. Safety, once again, just to remind you, is the property that nothing bad ever happens. And in this case of the election, safety says that for all non-faulty processes P, P's elected variable, which stands for P's vision of who the current leader is, should either be Q, a particular non-faulty process with the best attribute value. I'll talk about attributes in a little bit, but essentially assume that each process in the group has an attribute, say the IP address is the attribute. Right? We want to elect that process as the leader that has the best attribute value, say the highest IP address. So safety says that P's elected variable must point to that non-faulty process in the group that has the best attribute value, or P's elected variable points to null. In other words, P never makes a mistake and points its elected variable to a leader, a process that must not be leader according to the best attribute. Liveness property, again, informally speaking, liveness says that something good eventually happens. And in this particular case, the liveness property says that for all runs of the election run terminates, meaning that something, all the processes quiesce at the end. And then for all non-faulty processes P at the end, P selected is set to non-null. Okay, so P selected is not null at the end if P is a non-faulty process. So if you combine safety and liveness, this essentially says that at the end of the leader election run, which terminates, that process with the best attribute value is elected as a leader, and all the other non-faulty processes in the system have their local elected variables pointing to this newly elected leader. So what do I mean by electing the process with the best or highest election attribute value? Well, one of the most common attributes used is the highest ID. So among all the IDs in the group, you elect that process as the leader that has the highest ID. You can also reverse this and elect the process with the lowest ID in the group. That's fine too. Other attribute examples include IP address, they include fastest CPU, or you could use a disk space, or you could use, in peer-to-peer like settings, you could use processes that have the most number of files or the least number of files. As long as this attribute is fixed in the beginning and all the processes know about it, you're going to get a consistent leader election specification and a protocol as well. So in the next lecture, we're going to see a classical leader election algorithm, and then we'll follow that up by seeing a few more leader election algorithms.